Okay, so in this video, what I'm going to look at as an example of linear programming, okay? And this one is a little bit different than the previous one that we looked at. That had a very simple feasible region, meaning the x's and the y's, well, x went from 0 to 50 and y went from 0 to 50. And so that would just correspond to a square in the xy plane, right? X going between 0 and 50 and y going between 0 and 50 would be a square. For this example, what we're going to be looking at is a little bit more complicated of a feasible region and how we would find the maximum of this function that I have, 2y minus 3x, okay? So that's like either it could be thought of as profit or some other thing. It's just a function that essentially I'm wondering for any x and y, so I pick a point x and y in this feasible region, including on these boundary lines, okay? If I pick a point somewhere in this feasible region, I'm wondering what's the biggest that I can get out of this function by plugging in x and y, okay? So that's really what we're doing when we're doing linear programming, is looking for, well, what's the biggest, or sometimes if we're looking for a minimum, the smallest value that you can get by plugging in these different x's and y's for different points in this feasible region, okay? So to actually do this, okay, if you'll remember, we talked about last time this example of we had a plane, right? And we were finding the maximum profit, and x and y went from 0 to 50 on both, right? The maximum happened here, which was when x was equal to 50 and y was equal to 50. Now you'll notice, actually in the feasible region, right, that point is a corner of this square. It's the corner, you can't really see it on the screen here, but it's back in here, right? It's the corner of this square. As well, the minimum happens at the corner of the square as well, a different corner, okay? Now for linear things that you're dealing with, in other words, things where you just have x's and y's without exponents on them, without square roots, just with x's and y's times numbers and added together. If you have linear things, to find the max and min, they're actually going to happen at vertices of the feasible region, okay? So, oops, sorry, let me go back. So the max or min happens, it always happens for a linear function that you're maximizing at a vertex. Okay, so this is important. This is the main idea you need to take away from today, is that the max or a min of a linear function will always happen at a vertex of the feasible region, okay? So in other words, to find the maximum or minimum that this function achieves, all we need to do is look at the vertices of this region, okay? We talked about vertices last time. They're the points, kind of the corners of my region that works, right? So there's one right here, there's one right here, there's one right here, and there's one right there, okay? Those are my vertices of this feasible region, okay? Now, you probably can't see the scale on here, But this point here, this is at where the two axes meet. This is at 0, 0. Okay? So that's a vertice. Then there's one over here at 6, 0. Okay? This point right here, well, this is 1 and 1.5, so I think it's at 1.5 is my x value, and then my y value is, let's see, 2, and then 4 and a half. I think it's like 1.5 and 4.5, okay, is my answer there, okay? A lot of the time you won't get decimals, but in this one there is some decimals, okay? So this is just the coordinates of this vertice right here, okay? And then this other vertice, this one happens at 0 is my x value, and my y value is 2 and 3. So 0, 3 is my other vertice. So to actually find the maximum of this function, really all we have to do is care about the corners, okay? All I have to do is care about the corners. And so what I do is, we'll make a little table here, maybe. So we have x, y, and p, okay? So my first vertice, maybe I'll start with this one, okay? My x was 0, my y was 3. My second one, we'll maybe say is at 0, 0, okay? Third one is 6, 0. And then my last one, the kind of weird one, is 1.5 and 4.5. Those are my vertices of this shape. So now all I need to do is I just plug in the x and y of the vertice into this original function, okay, and kind of check between these which one is the biggest, okay? So I'm going to plug in 0 for x in here and 3 for y. So I do 2 times 3 minus 3 times 0. So we just get 6 there. Okay? If I plug in 0 for x and y, what happens? We just get 0. If I plug in 6 for x and 0 for y, I get 2 times 0, that's y, and then minus 3 times 6 is negative 18. Okay? Now this last one is maybe what's a little funky to deal with, right? We've got 2 times 4.5 is y, minus 3 times 1.5 is x, okay? So this would give us 9 minus 3 and then 4.5. So this would be 4.5, okay? So what did I do? I just figured out all the vertices of my feasible region, and I plugged those into the function, to the objective function, the thing I want to maximize, okay? And so when I do that, I look over here and I find the biggest number, because I want the maximum, right? So I had 6 was one number, 0 was a number, negative 18, and 4.5 were my final answers here, right? So which one is the biggest? Well, it's 6, okay? So this has a max of 6 at the point. What point gave us 6? It was at 0, 3. Okay? So in other words, if this was producing shoes, I would produce 0 of the first kind of shoe and 3 of the second kind of shoe. Okay? So this isn't that bad, right? All you have to do is find the vertices of your region and plug those into the function and compare which one is biggest. That is where the maximum happens. Now, if I was looking for the minimum, where would the minimum be? It would be the smallest, right? So this guy right here, this would be the minimum, right? Negative 18 is the smallest out of all of these, okay? So hopefully that makes sense. You can go ahead and try 2 of the homework problems that I have there on the page. Should be able to do that from this. And I will see you in the next video.